All right, so now we have this nifty parametric curve, and we know a little bit about what it means. What if we wanted to find a tangent line to it? And spoiler, we do. If we want to find the tangent to it, we'll need to know what dy dx is so we can get, a sense of the slope of the line of y as it goes in the x direction. All right, but here's sort of a problem, is that dy dx is not something that you get directly from x of t and y of t. Let's see, what do we have on this one? We had x of t is sine of 2t, and we had y of t is cosine of t. All right, so here's the problem, is if I just do the derivatives of these, they're not, if I just do the derivative of y, for example, am I going to get dy dx? I'm not. It's going to be dy dt is what is going to be negative sine of t. All right, and it's dx dt that's going to be equal to 2 cosine of 2t using the chain rule. Okay, so the question that we're stuck with is, how are dy dx, dx dt, and dy dt, how are they related and how are they different? What does it mean that I'm doing dy dt as opposed to dy dx? So look, t is a time variable. So dy dt means how is the y coordinate changing with respect to time? So as time goes forward, how does the height of the graph, well, I guess the graph goes this way. As time goes forward, all right, how does the height of the graph change? Well, the graph goes down and then it comes back up, and that's why dy dt is negative sine of t. All right, so it goes down and then it goes up. Okay, so how is that different from dy dx? So dy dx doesn't mean how fast is the y moving up and down as the point goes around. Dy dx means how is the y coordinate changing as the x coordinate changes. And it's a good way to really, get what this denominator in the derivative means. It means with respect to what variable are you changing? Am I talking about how y changes in time, or how the y changes depending on how the x moves? And those are different things, okay? And they're not immediately related. But they are related. So and how they're related is by the chain rule. So what it really comes down to is I have these functions x and y, and they depend on t. But to get dy dx, I need y as a function of x. All right? So how am I going to get y as a function of x? Well, what I have to really think of is that x also depends on t. So I know what y of t is, it's here, and I can say, well, that's equal to y of x of t. So I know what x is in terms of t, and I know what y is in terms of t. So if I want to think of y as it is in terms of x, I think of y in terms of x in terms of t. And that's where you can see that what you are really looking at here is a chain rule. And so that's the approach to getting what dy dx really is. All right, so now, you have to really think with respect to which variable am I doing the derivative. The derivative with respect to t of y of t. That's why this notation is very useful now. I don't want to just say y prime, because it's not with respect to x, it's with respect to t. All right, now the chain rule says I do the derivative of the outside function, but here's something we haven't mentioned before. It's with respect to what the inside function is. So the derivative with respect to x of y of x of t times the derivative with respect to t of x of t. All right, then we just want to recognize that this notation, this is what we mean by dy dt. It's the derivative with respect to t of y. d dx of y of x of t is what we mean by the dy dx that we are interested in. And the derivative with respect to t of x is what we write dx dt. All right, and then we just divide both sides by dx dt, and we get that dy dx is equal to dy dt, if I can write that, over dx dt. All right, now this is all you need to know about this in order to really work with it. But to really understand it, you want to understand what this is saying, that the rate of change with respect to x is equal to the rate of change with respect to y divided by the rate of change of x with respect to t. Did I say that right? The rate of change of y with respect to x is equal to the rate of change of y with respect to t divided by the rate of change of x with respect to t. Now, it's attempting in all these kind of analyses to say, oh, well, I mean, isn't that obvious because you could just cross the dt's? And the answer to that is no, it is not obvious because the dt's are not variables. So you cannot operate on them algebraically like variables. Now, it turns out what this result by going through chain rule is telling you is that it operates the same way as a variable in this case, but that does not constitute a proof of how these things interact. It really is almost more of an argument by analogy. You know, analogously to variables, you could cancel the dt's and get this. So it's a good way to remember the rule, but it doesn't constitute a proof of the rule. The proof of the rule really comes to the chain rule. The chain rule also looks like you could reduce the dx's, but if you recall what the book said about that when we were looking at chain rule, you cannot just cancel the dx's again because they're not variables, they are differentials, so they're really shorthand for a limit process. So if you want to prove that this is true, you have to prove that this is true. To prove that this is true, you have to go back to the limit definitions and really work with the limits, and the difficulty turns out to be that these two limits have different delta h's, and that's sort of the fundamental difficulty that makes the chain rule, which we're seeing here, or even here, difficult to prove, and we don't even prove it in this class or in this textbook. So if you're really curious about how to prove the chain rule, you can look that up online. There's probably a billion cool videos about it. I'd be happy to talk to you about it. However, it's not really the scope of our course. So what we're going to really focus on is that the derivative with respect to x is dy dt over dx dt. So in particular, for our curve, x of t equals sine of 2t and y of t equals cosine of t, we can say that dy dx is equal to our dy dt, which is negative sine of t, over our dx dt, which is 2 cosine of 2t. Now, be aware that you cannot simplify that because since the variables here don't match, we can't call this tangent or anything like it. All right, so this is how we're going to get dy dx for this curve, and in the next video we'll use that dy dx, or you could actually even anticipate and see how we're going to use this dy dx to come up with a tangent line. Let's see, where did we say we're going to do the tangent line? We're going to do the tangent line at t equals 0.6, and here's that formula nicely written for you. All right, so that's next. See if you can anticipate and get that tangent line before I do.